Unfortunately, my colleagues couldn't be here to present the work, so it's just going to be me presenting this presentation. So today I'm going to be talking mostly about how we can use non-volatile memory to accelerate big data processing. So we'll take a look at how NVRAM and non-volatile memory SSDs can be used in Apache big data projects. So let's start by taking a look at the general modern data center architecture. So you typically have a web server in the front-end tier, and the web server is accessed through internet by users. And the web server is typically backed up by a database, which can be either a MySQL database or any other database. And then it has usually a cache built on top of it, which is, let's say, memcached. And it can also have, in modern data centers, a NoSQL kind of database like HBase. So this is typically what the front-end tier looks like. And then you have a back-end tier where most of the data analytics takes place. So your MapReduce jobs, your Spark jobs, all these jobs are run in the back-end tier on top of HDFS, which is the main distributed file storage. So this is the typical sort of architecture in modern data center architectures. And the front-end tier is typically what you would say online processing, and the back-end tier is what you would say offline processing. So if you abstract out the big data components from this entire architecture, you sort of get something that looks like this. So here you have different Apache components like MapReduce, Spark, and HBase. And your user applications are typically built on top of these. And underlying these frameworks, you have the Hadoop distributed file system and RPC framework, which is handling all the communication and storage. So the distributed file system is used by all the components. So this entire model is very scalable. However, it's riddled with communication and I/O bottlenecks. So as an example, you can see that HDFS is a distributed file system, and data is obviously replicated to multiple different nodes. So you have a lot of communication that's happening here. And secondly, you need to ensure that data is persistent. So it needs to be flushed to disk, because you want fault tolerance. So here again, you have a lot of I/O operations that are taking place. And the whole ecosystem is very communication and I/O intensive. So there is a lot of opportunity here for optimization, particularly in communication and I/O paradigms. So here we will take a look at how you can use modern networking technologies such as InfiniBand, RoCE, etc., and how you can use NVMe SSDs, NVRAM to accelerate these different components. So before we go into that, let's look back into the drivers of modern HPC and data center architectures. So in typical data center and modern HPC clusters, you have usually multi-many core technologies. You have modern networking technologies such as InfiniBand. So InfiniBand and RoCE kind of networks provide this RDMA technology, which is remote direct memory access. So this allows one node to directly access the memory of another physical node, bypassing the entire OS stack. So this allows for very low latency networking. And this also provides a technology called single root I/O virtualization, which allows for hardware-based virtualization, which is especially useful in data center architectures. And in addition, you also have solid-state drives, NVMe SSDs, which are becoming very popular. You have non-volatile memory being deployed, and you have parallel file systems, etc. And many cloud services are providing actually these kind of platforms. So this is an overview of the high-performance big data project that we at Ohio State University have been working on for the last 6-7 years. So as part of this project, we have been releasing high-performance versions of Apache projects such as Spark, Hadoop, HBase, and memcached. And we have been releasing these software stacks from a long time. And for Hadoop, we have plugins available for the Cloudera and Hortonworks distribution as well. So these stacks are available for all kinds of networks, including InfiniBand, RoCE, and Ethernet. We recently launched support for Singularity and Docker as well. And our user base is steadily growing. We have about 285 organizations that are using our packages. So with these packages, we have seen significant improvement with existing RDMA plus DRAM-based designs. And now we're asking the question, like, what can be done with RDMA plus non-volatile memory? So what are the next opportunities that exist, and what are the next challenges that we can do something about? This is just a brief overview of the release timeline and downloads. So we have been releasing different software packages pretty regularly, and the download count has also been increasing. So now let's go and take a look at an overview of the non-volatile memory technology and SSD technologies that have been emerging. So non-volatile memory is basically byte addressable memory, but which allows for persistence. So both those things are very important because you want to have performance and you also want to have fault tolerance. So non-volatile memory provides this sort of paradigm. So if you take a look at what used to exist before, on the right-hand side picture over there, I don't know if it's clear or not. So you have DRAM, which provides latencies typically of the order of 1 to 10 nanoseconds. And you also have solid-state drives, which allow for latency of about 100 microseconds. So there's a big gap here in terms of latency that you have. Here's where non-volatile memory comes in. So non-volatile memory fills this gap and allows for latencies of about, I'd say, 100 nanoseconds or so. And it's a huge feature which can be used particularly in big data frameworks. So the huge explosion of data that we have in diverse fields is requiring fast analysis and storage. And this NVM is providing the opportunity to build high-throughput storage systems for these kind of applications. So the storage technology is rapidly moving towards NVM. So we have a lot of technologies emerging from Intel. So Intel has recently come up with the 3D X-point technology. And this is a step closer towards non-volatile memory. So like I said, it's an emerging technology. However, there is no commercially available solution for non-volatile memory yet. So we have different emulation mechanisms that are being used in the academic community right now. So these are the two most popular ones right here. So NVRAM can be used, obviously, as a byte addressable memory, and you can use direct memory APIs to access data inside NVM. And you also can use standard file system APIs to access data in the memory through block addressable APIs such as mmap, OpenRead, whatever. And on the left-hand side, we have mechanisms to emulate non-volatile memory as a block device. So here you typically have a virtual file system running on top of a block device, such as a RAM disk. And then you can add certain delay to emulate the NVRAM performance on DRAM. And on top of the virtual file system, you have your applications, which are typically built using the file system API, like read and write. Similarly, on the right-hand side, you have the way of emulation of accessing NVRAM through memory API. So this is the best way to access NVRAM because it allows you to directly read and write data from NVRAM using load and store APIs. So this is what is typically called DAX file system or direct access file system. So this allows you to access data in NVRAM through load and store APIs bypassing the CPU page cache and page translation unit. So you don't have a switch from user space to kernel space for accessing data in NVRAM. So currently, this is the fastest way for accessing data in NVRAM. And these are the two mechanisms that are popular for emulating performance for NVRAM, since there's no commercially available solution yet. So this is the presentation outline for today. We just covered the introduction. So now I'm going to present the NVMe-aware RDMA communication library that we're working on at OSU. And then we'll look at how this library can be used for big data analytics in Hadoop and also in MapReduce. And then we'll take a look at how we can use NVMe SSDs for optimizing different kind of stacks. And finally, we'll conclude. So we have this new technology. So what is the design scope with this new technology? As I said, you can use NVRAM as a block device or memory. And obviously, with the block device model, you have certain software overheads that exist with IO system calls. And you can also use the memory APIs to access NVM, but this requires an application redesign. Similarly, in terms of performance, the general estimation is that write performance of NVM is about 10x worse, and read performance is 1.5x worse. So you also need to consider these performance characteristics while designing any sort of framework with NVM. So finally, we also have cost as a factor. Because NVM is emerging technology, the cost is expected to be very high, especially more than DRAM. So the entire question that we ask is that how can we modify existing systems to efficiently take advantage of the non-volatility of NVRAM? Now, we all know that we can do RDMA communication directly on top of NVRAM, but we can also do RDMA communication on NVM directly. So this is a huge benefit because for communication, generally, you don't need to read data from disk into memory, and then you can communicate data using RDMA. But with NVM, you don't need to read data anywhere, so you can directly operate or do network communication from NVM. So depending on where the data is present on the server and client sides, we have different communication modes. So for example, we refer D2N as communication where the communication buffers for client are in DRAM and server are in NVM. And similarly, others are named as appropriately. So we have designed several communication primitives to actually achieve communication depending on where the data is present, and also optimized for different message sizes. So on the left-hand side, you see a send-receive-based protocol for communication over NVRAM, and this is typically what we call an ego protocol. So in this protocol, you have an application buffer either in DRAM or NVRAM, and this buffer is copied into a pre-registered buffer that has already been registered using the RDMA APIs. And this buffer is sent to the server using a send-receive-based communication model. And the server side will do a memcopy into the NVRAM buffer and do a seal flush so that it knows that the data is actually persistent in NVM. Then you can add a delay as well here to emulate the NVM performance. And on the right-hand side, we see the rendezvous-based protocol, which is an RDMA read-based protocol for communication over NVRAM. So here you have a RTS-CTS-based design, where the client first sends a RTS message, and the server is going to reserve an NVRAM buffer, and then directly read the message from the client side using an RDMA read. And again, it does a CL flush on the server side to ensure that the data is persistent on the server buffers. So these two protocols are what we designed for communication over NVM, and depending on the message size, you can select the appropriate protocol, and we'll see some results. So we actually emulated NVM performance using a latency-based emulation model. And here we have some results showing the performance of different communication modes. And we compare them to the performance when you communicate using DRAM to SSD. So as expected, you see that the performance when you communicate with DRAM to SSD is very bad. And that's because of the need to do an extra I/O operation. And if we take a look at the communication for different communication modes within NVRAM, we find that there is a lot of discrepancy in the performance. So this is because of the read-write performance gap in NVRAM, because the reads are much faster than the writes, about 10 times. So we find that NVRAM to remote NVRAM performance is the worst, which is about 10 times overhead compared to DRAM. And DRAM to remote NVRAM is about an 8 times overhead, while NVRAM to remote DRAM is only 4x overhead. Similarly, for the RDMA read-based emulation, we find similar results for different communication modes. And communication overheads for large messages are especially bad because of slower writes to NVRAM. And in terms of the communication primitives, we find that RDMA read outperforms send receive for large messages, which is the same as is observed in the standard DRAM to DRAM-based communication model. So now let's take a look at how this communication library can be used to accelerate HDFS and MapReduce. So the question is, why do you need persistence? And where can NVM help? So the need for persistence is pretty clear. You need to have persistence so that you can have fault tolerance and you can guarantee that the data is actually present there, and in case of failure, it's going to be there. And typically, this is an HDFS architecture. The figure on the right shows the architecture. So we have the client, which accesses the name node to locate the blocks. And then it directly contacts the data nodes to place the data. So data is replicated for fault tolerance, which enhances data locality and read throughput. And as you can see, that this operation is very communication and I/O intensive. And the existing communication is based on Java sockets. And then the data is typically persistent on SSD or HDD. So here, with NVRAM plus RDMA performance characteristics, the question is, like, how can we design efficient big data stacks? And secondly, because with RDMA plus NVRAM, we can directly do RDMA operations on NVM. So we don't need to do an extra read operation or write operation from disk. So there is another opportunity here which can be utilized efficiently. So we came up with a new design for NVRAM and RDMA-aware HDFS, which we call NVFS. So the main features are that the design includes RDMA over NVM, and we designed a specific protocol to use NVM with SSD as a hybrid storage. In our design, NVM can replace or coexist with SSD through a configuration parameter. So as a result, cost-effective NVM-aware placement policies are needed. And this is what we designed for Spark and HBase in particular. So let's take a look at the design that we have proposed here. So we proposed two designs. One, which is using the block API that NVM provides, and the other is using the memory API. So in the block design, which is NVFS-BIKIO, so we have RDMA communication buffers, which are allocated in NVRAM, and the communication mode is D2N approach. And these buffers are used in a round-robin manner, and data received in the NVRAM buffers is encapsulated in Java I/O streams and written to NVM through the I/O APIs. So the data is written to NVM using block API so that we can preserve the HDFS block format. And as I mentioned before, the block format does not provide you the best performance. So that's why we also designed a design with the memory APIs. So here also we have two sub-designs. So this design, the NVFS-Memio, is the flat architecture here. So here we have shared buffers for communication and storage. So the buffers are allocated in NVM and are managed in a linked list. So this design does not maintain the HDFS block structure, because what we have here is that the client will communicate data into the buffer, and that buffer is directly in NVM, and it's used as is. So the disadvantage of using this design is that you need all the buffers to be already registered for communication. And then the disadvantage, again, is that you have suboptimal read performance, because you need to find the packets of a particular block using scanning the linked list that you have in NVM. So we have another design with NVFS-Memio, which is what we call the block architecture. So here you have reusable communication buffers and separate storage buffers in NVM. And this maintains the HDFS block architecture. So here you can have efficient communication overlap, because while you're communicating one block, you can be storing the other block. So this provides constant time retrieval of blocks, and it's much faster than the flat architecture, because you don't need to go through the linked list in the NVM to find a particular block. You can use the hash table that's there, and it's more modular. So the main advantage here is that you have very fast read, and there's no need to register all the buffers for RDMA communication. So now let's take a look at the results. So we tested our Hadoop package on two different clusters, STSC Comet and the NowLab cluster. So here we're comparing the original HDFS performance with NVFS block IO and MEM-IO. For the MEM-IO one, we are using the block architecture because we find that it delivers much better performance for both read and write. So as we can see here, our design provides up to 4 times more improvement for write, and about 2 times improvement for read operations. And we have also co-designed with HBase and Spark. So here we're showing the HBase numbers. And we've taken these numbers using YCSP. And we're presenting the throughput numbers here. So here we optimized by only storing the write-ahead logs on NVM, because we want a cost-effective solution. So we only stored the write-ahead log on NVM. And we found that with the block I/O performance, we can about get 21 or 20% improvement compared to the default approach. So similar to HDFS, we have also found that a lot of opportunities exist for using NVM in MapReduce. So typically, this is the MapReduce architecture. You have map and reduce tasks. So the map tasks typically read data from HDFS. They operate on it, and they output the intermediate data to local disk. And then the reduce tasks get the data by shuffling from node managers. They operate on it, and they write data to HDFS. And the data has to be persistent, because you need fault tolerance. So this is, again, communication and I/O intensive. And shuffle is using communication over Java sockets. And I/O operations are typically in SSD or HDD. So you have bulk data transfer and heavy disk I/O operations. So there's a lot of opportunity. So let's take a look at where the opportunity exists. So you have a lot of data that the map tasks output, and it's placed on disk usually. And then the merge happens on disk, and then the data is sent using RDMA to the shuffle engine in reduce tasks. So this is the design that exists inside the current MapReduce RDMA package. So here, instead of placing intermediate data on disk, we can obviously place data on NVM, because the reduce tasks are all going to read data and put it in memory. So opportunities exist to improve the performance with NVRAM. So we find that using NVRAM for intermediate data provides a lot of good performance benefits. And then you can actually do a merge operation right on NVRAM data. So this minimizes the disk operation in spill phase. And secondly, because the data is in NVRAM, so the reduce task can directly read data using an RDMA operation, and that saves another disk read operation that we have to do. So now let's take a look at the results. So we have taken results for Sort and TeraSort. So we see that our design achieves up to 2.3x benefit for map phase, and overall about 55% benefit compared to the default design. And we also evaluated with Intel high bench workloads. So here we see for shuffle-intensive workloads about 42% benefit for Sort, 39% benefit for TeraSort, and 21% benefit for PageRank. And we also evaluated with the PUMA workloads. So here again, we find good performance improvements, especially for self-join, where we see about 58% performance benefit. So now we have taken a look at how we can optimize big data stacks using non-volatile memory. But the problem here is that all the results and designs here are based on emulation. So now we want to take a look at how we can design big data stacks using existing technologies, such as NVMe SSDs, which are something that have recently come into the market and become very, very popular. So let's start by taking a look at the overview of the NVMe standard. So NVMe is the standardized interface for accessing data over PCIe SSDs. So the new NVMe standard replaces legacy AHCI-based protocols for accessing data over disks. And this protocol has been based on RDMA-based principles, so it's by design high performance. So it uses submission and completion queues, and these completion queues generally rely on hardware-based queues that are available within the SSDs. And we have asynchronous command processing, and the important point to note here is that you can have up to 64K separate IO queues and 64K commands per queue. So you can have a large degree of parallelism that can be exploited by using this standard. So because of this, and the fact that NAND-based SSDs provide very good random reads, so you can have efficient small random I/O operations. In addition, the standard allows for MSI, MSIX, and interrupt aggregation, so you can deliver interrupts on completion of an I request to each individual core. So this significantly reduces latency of command processing and allows you to build very high performance storage systems. You also have another standard that's been introduced fairly recently, which is known as the NVMe over Fabrics protocol. So this allows you to access a remote flash device using any fabric. And in particular, we are interested with the RDMA fabric here because it provides very low latency, so it makes remote access almost of the latency of local access. So if anyone is familiar with RDMA primitives, this protocol is using a one-to-one mapping of the NVMe I/O queues to RDMA send receive queues, as shown on the figure on the top right. And the bottom figure here shows the general architecture of the NVMe over Fabrics protocol. So here you have a driver on the host, which is typically managing how data is accessed. And then you have the RDMA transport underneath. And on the target side, you have the NVMe target driver, which is communicating with the RDMA, the NVMe host driver, and accessing data to the SSD. So because of the low latency RDMA communication path here, you have very low latency overhead compared to local I/O. And this protocol allows you to build very large disaggregated storage systems with very good performance. So Intel has recently come up with a new library called SPDK, the Storage Performance Development Kit. So this provides high-performance storage I/O directly over the NVMe standard protocol. And we find that this protocol gives significant performance improvement over the POSIX NVMe driver. So even the POSIX API has support for the NVMe protocol, but internally it's using the NVMe standard APIs. However, it has very high software overhead because of context switches for every I/O call. And in addition, it is obviously operating in kernel mode, which provides very bad performance. In contrast, SPDK is providing user space, lockless, and port mode components, which provide significantly lower latency and higher throughput. So this library is available on GitHub, open source, and it has the potential of significantly improving any sort of big data framework directly by providing this new API, user space API. So now we've taken a look at what the NVMe standard offers. So let's take a look at the design challenges that exist within NVMe SSD. So the NVMe SSD provides you with a lot of features, as provided here in the gray box here. And these provide opportunity to co-design with application frameworks. So you can build very efficient file systems, cloud storage systems, or persistent caches, these new protocols. And now let's take a look at some of the exact challenges that exist. So for example, the NVMe protocol introduces hardware-based QoS. So you can have weighted round-robin or round-robin-based command arbitration, which can be directly done in hardware. And this provides opportunities to build new QoS-based systems. And in addition, for persistence, you need to be careful about if data is flushed or not, because SSDs typically have a write cache. So you need to ensure that the data is flushed from the write cache to the NAND chips so that the data is persistent. In addition, for performance, you need to take in regard that flash has a read-write performance queue and garbage collection overhead. So you need to design your system according to that. Finally, NVMe also has SRIOV hardware support. So this provides hardware-based virtualization and namespace isolation-based techniques. So this can be very good to use in cloud environments. So overall, I think the NVMe standard has great potential here, and it has the possibility of designing very good disaggregated storage with NVMe over Fabrics, persistent caches, and high-performance cloud storage systems. So we did a preliminary evaluation to test the performance of the NVMe standard, and we used the POSIX NVMe driver and the SPDK NVMe driver. And we used RocksDB, which is a Facebook-based key value store. So here we are providing results for the DB benchmark for insert, overwrite, random read, write sync, and read write. So here we see that using SPDK especially, we can get about 61% improvement compared to the POSIX driver. And we find that overwrite benchmark in particular is using compaction and flushing in background, so there is very little potential for improvement here. But we also find that read performance is much worse in SPDK. So we say that additional tuning and optimization is probably required here to improve the performance. Similarly, for throughput, we find similar performance trends. And particularly for read-write, we see up to 160% improvement in performance. So the important thing to note here is that both of these POSIX and SPDK are using the NVMe protocol underneath. But because SPDK is using user space, lockless, and polling mode components, it can provide significantly lower latency. So especially when you have such a new standard which is providing such good opportunity for performance, you need to reduce the software overhead as much as possible. So that's why it's important to use a library or design protocols which has very less software overhead. So in particular for NVMe, we find that this is a very important thing. And as I mentioned before, so we have been mostly focusing on the QoS challenge related to NVMe and how to use hardware-assisted QoS in providing bandwidth guarantees to applications. So as part of that, we have designed a new QoS-aware SPDK design. And we've been constantly working on this for the last year. So here we're showing the results for different application scenarios. So on the left here, we have the results for one application scenario where we are showing the bandwidth over time. So in this scenario, we have two applications running constant IOs with different priority. So as you see, the default design, which is the weighted round-robin design in SPDK, does not provide any bandwidth guarantees here. And the green and orange lines show that both jobs are given equal bandwidth. But using the new design that we developed, both jobs achieve disaggregated or differentiated performance. And on the right-hand side, we have the job bandwidth ratios that we achieve for different application scenarios. So in all of these application scenarios, we have two separate jobs running. And these jobs are typically running constant IOs with different request sizes. And here also we find that the default SPDK design falls short of achieving the desired job bandwidth ratio, while our design is very close to the desired job bandwidth ratio. So to conclude, our design is generally providing very close to the desired job bandwidth ratio, and we find it has very stable and consistent bandwidth. So we've been working on this for the last year, and we have submitted a paper which is currently under review. Finally, to conclude, so our work has mostly been based on NVMe-aware RDMA-based communication and I/O schemes for big data. And in this work, we proposed a new library called NRCIO, which is a work in progress. Using that library, we redesigned the HDFS and MapReduce components in Hadoop. And then we have also been recently looking at big data analytics stacks redesigning with NVMe and NVMe or Fabrics protocols. So we find that the initial results are quite promising. As we show it from the results, we can see good benefits using NVM and NVMe. And there's obviously scope for future work here. Further optimizations are being done in the communication library. And we hope to co-design our library with more big data stacks in the future. So with this, let me conclude, and I'll be happy to take any questions. Yes.
In your baselines with the HDFS benchmarks,
Yeah.
is it based on hard disk, SSDs?
So I think we took the baseline with SSDs.
So it was with SSD.
Yeah, it's PCIe SSDs, Intel.
And the second question is, you said the cost of NVM is more
Mm-hmm.
than even DRAM, right? Like, is it cost per byte? And what capacities are we talking?
So our results are based on emulation, because you don't have any commercially available solution yet.
I see.
But yeah, the expected cost is generally supposed to be higher. So Intel is supposed to release the NVDEM package this year. So we'll probably see what the cost looks like. Yes.
What was the network protocol that you used to transfer data between DFS client and the data node?
Oh, so we're using RDMA-based protocol. So it's using an InfiniBand network, if you're aware.
So, on the, so 32 machine cluster means that it's probably on the same RAM, right? So what happens with this protocol if you need multiple RAMs?
So let me go back to that result. So you're talking about this result, right?
Yes.
So these were taken on STSC Comet, which is a supercomputer. So typically, you would not get nodes which are on a single rack at any time. It's highly unlikely that you would get a set of nodes on a single rack. So most likely, these results are on nodes which are on different racks.
This is just to follow up on Vinod's question.
Sure.
So the benchmarks in which you ran the DFS benchmark, right? So are you confirming that there are no hard disk cut out only NVRAM and RDMA? Like data nodes are backed by here.
Data nodes are backed by SSD.
Only NVRAM.
Sorry?
Data nodes were running only with the NVRAM, right? There are no hard disk or SSDs.
Oh, on that node? Yeah.
Not in the results. Could you go back? Yeah. One before. Where you did DFS benchmark. And where it was.
DFS benchmark? Is it this?
It's this one.
Yeah, it's this one.
Yeah, so what's the first entry there? Is it HDFS? That you answered. It's
Yeah.
HDFS with SSDs.
Mm-hmm.
And then you went to NVFS-BIKIO.
Yeah.
It's NVM emulation on top of it.
NVM emulation on top of DRAM.
On top of DRAM.
Yes.
Yeah, so this one.
Yeah.
When you are analyzing the performance benchmarks, did you look at the saturation of the resources? Because sometimes the scheduling can be a factor in the performance results here.
Mm-hmm. So what kind of resources?
So, like with the hard drive or SSD, the I/O throughput is already saturated during the test on versus not. Sometimes it's not enough threads like saturating the hardware, but sometimes this kind of thing can be affecting performance, right?
Yeah, I don't think we checked that, but I would have to get back to the developer of this library to check. Yeah, it's a good point. Thanks.
So does the baseline enable RDMA or not?
So the baseline, I'm not sure. Yeah, I don't think the baseline is using RDMA.
Okay, it's not.
It's not using RDMA, yes.
And the second question, so you mentioned it's not really helpful in the RocksDB adaptation scenario. So do you have more details? Do we know why?
So for RocksDB, basically we find that, especially for overwrite, the compaction and syncing is happening in background. So you won't see any benefits, obviously, from using SPDK. And for read, we find that the internal design, which is built on top of SPDK, currently has some bottlenecks. So if you optimize those code paths, then you can possibly have better performance.